In 1970, a program started by the Soviet Union that became known as the Kola well, or the Kola borehole, got started on the Kola Peninsula in Russia. The goal of this project was to drill down as deep as humans could go. That was the sole purpose of this project. On the third try, they ended up getting down to 12.3 kilometers down. That is deeper than the deepest active mine by a long shot, and it's deeper than the Marianas Trench in the ocean. The program was later abandoned in 1995 when they ran out of money, and they also realized that the temperatures at that depth were way too hot for them to continue drilling. The temperatures got up to 180 degrees Celsius, or about 350 degrees Fahrenheit. That's really dang hot, and it's way too hot for rocks to behave brittly. They start to become plastic, and they don't respond to the drill equipment the way that they are supposed to. Today, that borehole is sealed shut, as you can see in the picture here in the top left. But people still go and visit this location just to see what's there. Some people think it's haunted. And the structures that used to be above the borehole are pretty much destroyed. So this borehole was a huge achievement for mankind and still remains the deepest hole we have ever dug. It's actually not that deep. Overall, it ends up being just 0.2% of the way to the center of the Earth. So we have a long way to go. And that also means that we still haven't observed things like the mantle. We never made it to the mantle. We haven't seen the outer core or the inner core. We haven't observed these things directly. So how do we know all that we know about Earth's mantle and outer core and inner core if we haven't observed it directly? We're going to talk about some of the methods that lead to what we know about the composition of Earth today in this lesson. So I'm going to be talking about Earth's interior, right? What Earth is composed of, what makes up Earth, and how we know those things. I'm going to dive into what it's made of and how we know it. We'll talk about the temperature of Earth, Earth's magnetic field, as well as isostasy and what that means for Earth's crust and how Earth's crust behaves. So let's talk about how we know about Earth's interior. So the things that we haven't observed directly, we haven't looked at the mantle, we haven't looked at the outer core, etc. So I'm going to review Earth's compositional layers. So remember that Earth is made up of layers that have different compositions, different rock materials, right? So there's the crust, which tends to have an intermediate to a felsic overall composition, and it's about 5% sedimentary rock. The other 95% is metamorphic or igneous. The mantle is overall an ultramafic composition, so beyond mafic, it is more of a peridotite composition. The outer core is liquid iron, and the inner core is generally solid iron. The mantle specifically is pretty complicated, and there are some important layers or boundaries within the mantle that I want you to know. The lithosphere is it contains the crust in the uppermost part of the mantle, and it behaves solidly. So the thing that's going to differentiate some of these layers from the compositional layers is their behavior. So these have different mechanical properties, and I talk about this in another lesson. I think it's important to know the difference. The lithosphere is generally solid, behaves in a solid fashion. The asthenosphere, which is the part of the mantle just below the lithosphere, is partially liquid. This is pretty important. It's going to behave differently than the lithosphere because part of it has already melted. The upper and the lower mantle are generally solid but plastic, so if the rock deforms, it doesn't deform permanently. It's not that important to know, except that it doesn't break. It's under so much pressure and it's under so much, there's so much heat down there that it tends to behave plastically. But there are different minerals present in the upper and lower mantle, so there's a compositional difference between the upper and lower mantle. The D double prime layer is kind of interesting. It is also partially liquid, and it's a low seismic velocity zone near the lowermost 200 kilometers of the mantle. There's also the core mantle boundary, which is about 2,900 kilometers down, and that's what divides the plastic mantle from the liquid outer core. So that's the bottom boundary of the mantle. So how do we know about these different layers within the Earth? We learn these things through seismology, which is the study of vibrations
on Earth or within Earth that are caused by all sorts of things, including earthquakes, any sort of impacts by meteorites or other things, explosions, storm waves, tidal waves, etc. Obviously, seismology is often understood as the study of earthquakes, but there are lots of vibrations within Earth that can give us clues as to what is going on below the surface. When a fault within Earth's crust slips or fractures for the first time, there is usually a release of energy, which comes in the form of earthquake waves. We are mostly concerned with body waves, including P and S waves, when we're trying to understand Earth's composition. There are lots of other types of waves, but these are the ones that give us clues as to what Earth is composed of. So let's talk about the difference between P waves and S waves. P waves are what we call primary waves. They're the first waves to arrive if you say you have a seismometer, you have an instrument that is detecting vibrations within the Earth. Those primary waves are what arrive first. It's essentially a seismic body. And this definition sounds complicated, but it's really not. It's a seismic body wave that is characterized by deformation of the rock in the same direction that the wave is propagating. So it's a compressional vibration. It's if you were to take a slinky and you were to compress it and sort of push it, right? So those would be compressional vibrations. S waves, on the other hand, are the secondary waves. These are slower and they arrive second to the primary waves. So these are a seismic body wave characterized by deformation of rock that is transverse to the direction that the wave is propagating. So it's not a compressional wave. It's more of like if you were to take a slinky and like jiggle it back and forth. Those would be the waves that most resemble an S wave. Now, the speed at which these waves travel through different materials is what gives us clues as to what Earth is composed of. It's all about the speed at which these waves are traveling. And we have seismometers all over the Earth now, and so we're able to observe when an earthquake occurs or an impact hits the Earth, or we can sense tidal waves and things like that. But earthquakes are kind of a primary example of how we make these observations. If an earthquake occurs from that focal point to where the waves are sensed, if you calculate what the velocity is of both the S and the P waves, it's going to give you a clue as to what sort of material those waves were traveling through. Generally, these waves both travel faster in more dense rock, such as mantle rocks. Mantle rocks are more tightly compressed than crustal rocks. There are no spaces in between them. They're under a lot of pressure. And waves tend to travel slower if the rock has some melt in it. S waves in particular, this is really important. S waves will stop completely if the material is completely liquid. So if we were to sort of map out the speed of these seismic velocities and how they are related to depth from the surface, you can see that they go relatively quickly near the surface of the Earth. Then they encounter an area of low velocity. This is the asthenosphere, this area where they slow down a lot. Then they speed back up again. When the waves encounter the core mantle boundary, the bottom of the mantle, that's when they slow down a ton. In fact, S waves disappear completely. Why? Because the outer core is liquid, right? Those S waves drop out entirely. The P waves slow down dramatically. Then they'll pick up once again in the inner core where it's solid. It's also important to note we have a pretty good understanding of the velocity at which these waves propagate through different earth materials, from dry sand and clay to wet sand, mudstone, sandstone, granite, basalt. We have observed a lot of waves traveling through lots of different materials. We can do this in the lab, and we can calculate exactly how quickly these waves are passing through different materials. And as you can see, primary waves are always faster than secondary waves. There are a couple other interesting features of these waves, the S waves and the P waves. These waves tend to be diffracted, or they tend to have a curvature to them. This is because they're passing through different materials. If the material of the Earth was all the same, they would just pass through in a straight line. But because they're encountering different densities, those curves, or their path tends to be a curved path. These waves tend to be diffracted toward less dense material, which happens to be towards the surface of the Earth. So these waves all tend to curve upward toward the surface. S waves stop at the core mantle boundary because the outer core is liquid. Those S waves can't propagate through the liquid core, so they stop entirely. This forms what we call an S wave shadow. So you can see here on the left that this red zone right here, no S waves from an earthquake occurring on this side of the Earth will make it to the other side. And that's because of this S wave shadow. They can't propagate through that liquid core. P waves, on the other hand, they can propagate through the liquid core, but they get refracted in such a way that they have these really weird refraction patterns. And there's also a shadow zone for P waves, and there are two locations where P waves won't appear on the other side of the Earth from the epicenter. And those two shadow zones occur in these small zones here. It's only about 50 degrees, a 50-degree angle. The waves are also refracted, as I mentioned before, at boundaries like the MOHO, which I'll talk about in a moment, and the core mantle boundary, or the bottom of the mantle, as well as the outer core and the inner core boundary. So anytime the composition of the Earth changes, those waves are going to get refracted. So I want to talk about the MOHO, which is an interesting boundary within the Earth. It's the boundary between the crust and the mantle, and it was first discovered in 1909 by a seismologist, a Croatian seismologist named Andrija Mohorovičić. I hope I pronounced that right. And it became known as the Mohorovičić discontinuity, or the MOHO for short. And this, again, is the boundary between the crust and the mantle. And this seismologist used exactly these things that we've been talking about, these seismic waves, to determine that there was some sort of boundary. There's some reason why those seismic waves are being refracted up toward the surface. He noticed that one set of seismic waves was arriving faster than another set of seismic waves, even though it was traveling a further distance. So the velocity was faster in waves that happened to be, what he discovered, waves that were traveling through the mantle, which is denser than the crust. So those waves, even though they were traveling further, were traveling faster. So that's how he was able to calculate where this discontinuity, or this boundary, was between the crust and the mantle. This boundary typically occurs at about 30 to 40 kilometers beneath most continental crust. The continental crust is pretty thick, generally, and about 5 to 10 kilometers beneath oceanic crust. Oceanic crust tends to be much thinner. Now let's talk about Earth's internal temperature. So Earth has a geothermal gradient, or what we call the geotherm, and this is how the temperature of Earth increases with depth. As you go down, Earth gets hotter. As the folks working on the borehole, right? What they figured out was that it does indeed get very hot the further you go down into the Earth. But this increase in temperature isn't linear. So if you look at this plot here, we have temperature increasing to the right and depth increasing as we go down. It's fairly consistent for a while until you get through the asthenosphere, and then that temperature doesn't increase quite as quickly with depth. One thing that I want to point out is that there's sort of this zone that we know as the asthenosphere, and the reason why we have designated the asthenosphere, or this low velocity zone, is because it is different than other parts of the mantle. The asthenosphere is this zone where the liquid solid boundary here for mantle rock gets very, very close to the geotherm. So this black line is the geotherm here. Those lines get very close together In fact, at some locations they may intersect. And what this means is that the rocks are getting hot enough that they can partially melt or even melt completely. And in terms of seismic waves, this means that those seismic waves traveling through are going to slow down a whole bunch when they hit the asthenosphere. So that's why it's also known as the low velocity zone, because the velocity of the seismic waves slows down. So just to recap, in general, the mantle isn't molten except for in this one special area within the asthenosphere where that liquid-solid boundary gets very close to the geotherm. There's also a quality of the mantle that's pretty interesting, known as convection. And the way that we know this is if we look back at this diagram here, you can see that the mantle is hottest when it's nearest to the outer core. So the highest temperatures in Earth are within the core, right? The mantle is also really hot the closer it is, the closer you are to the outer core, and it cools down the further you get away. This characteristic led scientists to believe that there's convection occurring within the mantle, and there's a lot of evidence for this now. Basically, what's happening is the mantle rocks get heated up the closer they are to the outer core, and they become less dense, kind of like our lava lamp example, right? As those blobs fall and get close to the heat source, the lamp's heat source at the bottom, they get reheated, they become less dense, and they float to the top. So this sort of convection is happening in the mantle as well. Another example of convection would be if you were to fill a pot of water, let's say you're preparing pasta or you're going to hard boil some eggs or something. You take a pot, you fill it up with water, and you put it on your stove. Then you turn the heat on. Well, the heat source is at the bottom. You can imagine that heat source is similar to the outer core where it's really, really hot, and it begins to heat or convect the water above it, or the mantle above the outer core, right? So the closer the water is to the heat source, the warmer it gets. It's going to become less dense and rise to the surface of your boiling pot of water. When it rises to the surface, it cools down and then sinks back down. So you get these convection currents that are cycling the water through. Same sort of thing is happening in the mantle. And this process is really, really important to plate tectonics, which we'll get into in a different lesson, but it's a really key characteristic of plate tectonics. It's also important to note that mantle convection, this process is going to stop when the core has cooled enough. This won't happen in my lifetime or your lifetime, but it will happen eventually. The cores have already cooled on planets like Mercury, Mars, and our own moon. There's no more of this convection happening within those planets or our moon. Next, I'd like to cover Earth's magnetic field. This is pretty interesting because it has a lot of effects on how we experience life on the surface of the Earth. And it also has some implications for the rock record and also dating rocks and understanding where those rocks were in the past. So Earth, as you know, has a magnetic field. Its south pole, its geographic south pole is technically the north end of that magnet, and Earth's geographic north pole is technically the south end of the magnet. But regardless, there is a magnetic field on Earth. And that has to do with convection within the liquid iron outer core. So we talked about convection happening in the mantle, but there's also convection happening in the outer core where it's liquid. Because it is iron, the convection of that iron is what's producing our magnetic field. This isn't a stable magnetic field, though. It's not consistent over time, and it tends to change periodically. We have evidence of Earth's magnetic field flipping many, many times over Earth's history. And the reason we know this is because many minerals have a magnetic quality to them. And as igneous rocks cool, the magnetic minerals within those igneous rocks will align themselves to whatever Earth's magnetic field is at that time. So it is a rock record. There's a record within the rocks of what Earth's magnetic field was at the time that those rocks cooled. Most geologic timescales will also include some sort of magnetic record of what the polarity of Earth's magnetic field was like over time. And you can see that during the Cenozoic, Earth's magnetic field has flipped numerous times, but it was really stable during the Cretaceous. So like I said, these reversals happen pretty often, and they're really random. We don't yet have an explanation for why these happen when they do. We can use this process of studying magnetic minerals within rocks to also more narrowly determine the age of rocks, particularly igneous rocks. This is really handy because you can't use relative age dating always with igneous rocks. So paleomagnetism is a really useful tool for sort of narrowing down when we think those igneous rocks intruded. So this is another method for determining the age of rocks. Okay, finally I want to talk about isostasy. Isostasy is essentially the equilibrium between a block of crust floating on the plastic mantle. Isostasy can be applied to lots of different concepts, but in terms of earth science, we talk about isostasy mainly with Earth's crust and mantle. The mantle is plastic, and in your text they talk about the mantle being made of a material kind of like peanut butter, something viscous, and the crust is sort of floating on top of that plastic mantle. It's not resting on top, the mantle is not solid, but it's kind of sinking down into the mantle. The thicker that crust is, the lower it's going to sit in the mantle. So a good analogy for this is a cargo ship. If that cargo ship is empty, it's going to sit higher in the ocean. But once you load it up with cargo containers, it gets much heavier and it's going to sink lower and it's going to displace more water. This is really important when we're talking about erosion. So if you have a very thick crust, say you had mountain building in this region, but then over time that surface was eroded, you are decreasing the thickness of the crust. It's getting thinner. And therefore we're going to experience what we call crustal rebound. And that is when Earth's crust sort of rebounds back up once the thickness has been decreased. Similarly, something like this happens with deglaciation. So if we have a thick layer of glacial ice on top of the crust, that's putting a lot of extra load on the crust, so the crust sits further down in the mantle. But once that ice melts, the mantle and the crust both will rebound in a process that we call isostatic rebound. So this can happen, again, if you're eroding mountains or if you're removing glaciers. Okay, that about wraps up our discussion of Earth's interior. There are a lot of interesting characteristics of Earth, and we could go on for days about this, but I hope this gives you a general overview of what Earth is made of and how we know that, even though we haven't been able to observe anything below 12.3 kilometers, right? I also hope you learned a little bit about the temperature of Earth and Earth's magnetic field and how isostasy works. Thanks for watching, and I'll see you in the next video.